Hey, welcome. Ever stop and think about what's holding the world together? I mean, literally. From a huge steel skyscraper to the tiny grains of salt on your fries, everything is held together by these powerful invisible forces. Well, today, we're going to decode two of the most important types of this atomic glue: metallic and ionic bonds.
So let's start with something you definitely have in your kitchen. Good old table salt. It looks pretty simple, right? Just tiny white crystals. But if we could zoom in way down to the atomic level, there's this incredible story of attraction and stability playing out.
So what is it? What's this invisible glue that locks all those tiny particles together so tightly that you can actually hold a salt crystal in your hand? To figure that out, we've got to start with the basics. We need to understand what a chemical bond actually is. At the heart of all this stickiness, you'll find a fundamental force that runs the show on the smallest scales of matter.
A chemical bond, when you boil it all down, is just an electrostatic attraction. You know how opposites attract, right? It's pretty much the same idea. It's the force between positive and negative charges that pulls atoms, or their charged-up cousins called ions, together. Let's see how this whole thing works in metals.
Okay, think about any metal you can. Iron, copper, gold, you name it. They all share this really unique type of bond that explains why they're so strong, why they're shiny, and why they're such great conductors of electricity. It's called the metallic bond.
So here's what happens inside a metal. The atoms basically agree to give up their outermost electrons. These electrons become, and this is a key word, delocalized. That just means they don't belong to any single atom anymore. Instead, they form this free-flowing sea of negative charge that moves all around a fixed grid of positive metal ions. The metallic bond, that's the super strong attraction between that negative sea and all those positive ions. Now, this whole sea idea is the secret to one of the most important features of metals. Because that sea of negative electrons surrounds the positive ions from every angle, the attraction pulls equally in all directions. It's not a rigid one-to-one connection. This is why if you hit a piece of metal with a hammer, the layers of ions can actually slide past each other without shattering. That sea of electrons just keeps holding everything together. It's what makes metals malleable and ductile. Pretty cool, right? All right, let's switch gears. We're moving from that collective sea in metals to what happens with individual atoms. Because before we can really get our second type of bond, the ionic bond, we need to see how a regular atom turns into an ion in the first place. It all comes down to one thing: stability. See, most atoms out there aren't stable. They have this need to get a full outer shell of electrons, just like the superstable and kind of snobby noble gases. To make that happen, a neutral atom will either lose or gain electrons. As soon as it does, that perfect balance between positive protons and negative electrons is gone, and bam, it becomes a charged particle, an ion. If it loses electrons, it's left with a positive charge, and we call it a cation. If it gains electrons, it gets a negative charge, and we call it an anion. And this whole process of losing and gaining electrons, that's the key to our main event, the creation of an ionic bond. This isn't about sharing electrons in some big sea. No, this is about a direct, dramatic transfer. So, let's meet our two main players, who, when they get together, make table salt. Over here, we've got a sodium atom. It has one lonely electron in its outer shell, and it desperately wants to get rid of it to become stable. And on the other side, we have a chlorine atom. Its outer shell is almost full, it just needs one more electron to be complete and stable. I think you can see where this is going. And there's the action. The sodium atom just gives its outer electron away to the chlorine atom. It's a total win-win. In that one single act, both atoms get exactly what they want. Sodium becomes a stable positive ion, and chlorine becomes a stable negative ion. This transfer is what creates two oppositely charged particles right next to each other. That transfer is what creates the bond itself. The brand new positive sodium ion and the negative chloride ion are now powerfully electrostatically attracted to each other. That force holding them together is the ionic bond. And let me tell you, it's an incredibly strong attraction that locks them into that rigid crystal structure we see as salt. Now, you'll hear this all the time. Since metals like sodium tend to lose electrons and nonmetals like chlorine tend to gain them, it feels like ionic bonds must always be between a metal and a nonmetal. It seems totally logical, but is it actually true?
Nope, not always. This is a classic misconception, a really common trap to fall into. And while it's a very common pattern, for sure, the real rule isn't about metals and nonmetals. The actual definition is way more fundamental.
Just take a look at ammonium chloride. The anion is chloride, Cl-, a classic nonmetal ion. But check out the cation. It's ammonium, NH4+. That's 1 nitrogen atom and 4 hydrogen atoms, all nonmetals that have grouped together to form a positive ion. So here's the real takeaway. An ionic bond is the attraction between a cation and an anion, period. It doesn't matter one bit what those ions are made of.
Okay, so now that we know what these bonds are, we've got to learn how to speak their language, how to write their names, and their chemical formulas. Luckily, there's a really simple trick for this called the crisscross method. Let's just walk through it with aluminum oxide. First step, you write down the ions and their charges. So that's Al3+ and O2-. Step 2, you take just the number from each charge, so the 3 and the 2, and you crisscross them to become the subscript for the other ion. So the 3 from aluminum goes down by the oxygen, and the 2 from oxygen goes down by the aluminum. Step 3, just write out the final formula, smushing it all together and dropping the charges, and you get Al2O3. It's a fantastic shortcut that makes sure your final compound is always electrically neutral.
Okay, so we've been talking a lot about these invisible, charged particles called ions. But how do we know they're actually real? Can we see them? Well, not directly, no. But we can absolutely see the proof that they exist. We can even see them move.
Our first clue is color. A lot of ions have these distinct, really beautiful colors when you dissolve them in water. You know that famous bright blue of copper sulfate solution? Well, that's literally the color of the copper-2 ion itself. That super vibrant purple of potassium permanganate, that's all from the permanganate ion. These colors are direct, visual evidence that those specific ions are in there.
But we can do even better with a classic experiment. You take a U-shaped glass tube and fill it with a colored ionic solution, like our purple potassium permanganate. Then you apply an electric current. You put a positive electrode on one side and a negative one on the other. And guess what happens? You can literally watch the purple color, which we already know is the negative permanganate ion, start to migrate, to move through the solution towards the positive electrode. Its opposites attract, happening right in front of you.
This is just incredible when you think about it. It's not some abstract theory in a textbook. This is visible, moving proof that ionic compounds are really made of separate positive and negative particles, and that they move exactly how we'd predict in an electric field. The abstract becomes real. So let's wrap this all up with the key takeaways. First, chemical bonds are the fundamental electrostatic glue holding our world together. In metals, that glue is a non-directional sea of electrons. In compounds like salt, it's an ionic bond, which forms from the complete transfer of electrons, creating this powerful attraction between oppositely charged ions. And finally, we know these ions are real because we can see their effects, from their amazing colors in solution to their actual migration on command.
And that leaves us with one last thought. We've seen just how strong the attraction in an ionic bond is. I mean, strong enough to form solid, stable crystals of salt. So just think about this. What kind of incredible energy would it take to overcome that force and actually melt that salt? Well, that's a story for another time. Thanks for joining me.